may be Fn with respect to f. Okay. So sometimes later on it can be useful to relabel this pre-image Fn as omega n, right? But I think for the time being it's good to do it like this. Okay, so this is no big surprise. This is precisely what we want. And if you remember from Lebesgue theory, if we had a real valued measure in Lebesgue theory, we had f d mu equals, and then we have Fn mu and this. Okay, this is just what this means. Okay. So two quick observations. So first of all, any characteristic function psi omega for a measurable set, a well-measurable set, is simple. So obviously only takes the values 0 and 1, and hence we can look at integral r psi omega dp. Okay, and what is it? Well, it is 1 times p omega plus 0 times the complement. Well, 0 times is nothing. So you integrate over the characteristic function p, you get back the p of omega. The other thing is what happens if you sandwich the integral between a psi and a phi. For any psi phi in H, so we construct integral f dp, and that's then a bounded linear map. So if it's a linear map, you can apply it to a phi in H. Then you get an element of H, then you can take the inner product with another element psi of H, and you can look at this complex number, right? So let's work this out, what this is. This is, of course, psi comma, well, we use the definition, sum over the n's, 1 to n, Fn times p of, well, now I call this omega n to not bite too much, so let me call this here omega n, okay, acting on the phi. But, well, you can pull all of this out. This is sum n equals 1 to n. You can pull out the Fn, it's from the second factor, so it pulls out like this. And then you have psi comma p of omega n phi, right? Do you remember how this guy was called? This guy was called mu psi phi of omega n from before. That's the sandwiching of this guy. And if you use that, you see that this whole thing is nothing but f d mu psi phi. So really you can look at the operator valued integral f dp, or you can look at its matrix elements, right? It's just a way of speaking, at the sandwich between two Hilbert space elements, not a matrix. And it's f d mu psi phi. And so here we reduce this to, well, a complex measure, Lebesgue integral, which maybe if I had written it from the beginning like this, you would know okay, why I know how to calculate this. And it's nice that it reduces to that. However, we wasn't able to reduce it like this, so I rather introduced it in real and have this as a theorem. Okay. So now comes an important proposition. So now we look at the following object. Integral dp. Not f dp, but integral dp. And I want to understand this symbol as a map. Now what does this map do? If there was an f dp, it would be a map from H to H, right? If the f is simple. But now I don't provide the f. That means this guy first needs to eat the f. And so far, the f's that can be eaten are the simple f's, right? Because that's what we defined so far. So this eats a simple f. And maps it to, well, this guy acts on the f, and I define this as FDP, right? So it acts on f, but then I let the f jump here. That's what I mean by this, okay? It acts on the f, FDP. And what is this FDP? Well, this FDP, so the result of this map, is a bounded map on f. Now, we know this, well, look at the definition. It's a finite sum of bounded maps. It's a bounded map, okay? Because the p is bounded. But you see, as such a map that first has to eat an f, you can now look at these two spaces, and you know that this space here, that it's equipped with the operator norm, equipped with operator norm, which we just call like this, or sometimes with the subscript, and we know this is a Banach space, remember? It's the Banach space of, it's the Banach space of bounded functions. And this guy here, you can actually make into a normed space. Obviously, the sum of two simple functions is simple, and a scalar multiple of a simple function, a complex scalar, so this is a complex vector space, and you can make it actually into a normed vector space by establishing the supremum norm. You remember the supremum norm was the f that takes just the supremum of all the f of x for x in wherever this comes from, R, okay? So it's the supremum norm that makes the space of simple functions a normed space. So we go from a normed space to a Banach space. Remember that situation going from a normed space to a Banach space? That was precisely the situation we looked at in the beginning on day 1, or actually lecture 2. So my claim is, so this is just remarks, so the claim, well, proposition that says, that is a linear map. What does that mean? Well, it means that integral dp equal an f and equal a sum f plus g, so let's write this in a more human way, equals integral f dp plus integral g dp, and alpha f equal alpha f dp is alpha integral f dp. So it's a linear map if it acts from here to here, and once it acted, the come out are also linear maps. Okay? When in the beginning I said that linearity is lost once we go from the simple f, if we drop the simple f, so if we drop the boundedness of f, we're not there yet, I meant we lose the linearity of this arrow. In here, this is a match from h to h, there's another arrow in here. The linearity of that arrow is never lost, and it's the linearity of that arrow that will be lost. Okay? So don't get confused by what I said at the beginning, so I want to emphasize this again. So this is a linear map with operator norm, integral dp norm equals 1. But that's not this operator norm, it's the operator norm being an operator from here to here. Look very carefully from there to where the map goes. Right? Okay, so that's the statement. Well, let's look at why this is true. So proof. So linearity is clear. Clear from the definition, because we have these finite sums and blah blah blah, that's clear. What we need to calculate is this norm. Calculate integral dp acting on f, dp acting on f, but we really want to write this as f dp, and then the result can act on a psi in the Hilbert space. So let the f be simple, and let the psi be, hang on, do I want it like... Yeah, I do. And the size from the Hilbert space. So let's calculate this guy. What is this? Let's calculate the square of it. The square of this is the inner product, integral FDP acting on psi, integral FDP acting on psi. Because that's the norm squared. This equals, well, because f is simple, this is the sum n equals 1 to n, fn, p of omega n. Omega n's I defined before, acting on the psi, but I can put it into the sum, it doesn't matter, comma, n equals 1 to the same capital N, fn, p of omega n acting on the psi. Okay? And now, of course, I can take this over here because, thinking of it like this, because it is a, the sum of these bounded adjoint operators is, of course, bounded and it's adjoint. So this is the sum of n equals 1 to, precisely, n equals 1 to n equals 1 to n, fn, but this comes, hang on a second, fn, aha, but I take this over here, but this p gets a star as the p again, but fn gets, of course, a bar. Fn, and then p of omega m, p of omega n, acting on psi, right? That means I take the maximum norm on this space, and here, of course, the maximum this can take is the psi, the absolute value of psi on the Hilbert space. And once you have that, you can calculate the operator norm of the map integral dp. Not of the map integral FDP, but of this map integral dp. You can calculate the operator norm. And that operator norm will be given in terms of another operator norm, which you can then reduce. Yes? Because these are projections, and we have, if omega n, this thing equals, okay, I should have an intermediate step. We saw that this equals p of omega n intersected omega n. Yeah, okay, thank you. Okay, so thus we can calculate the operator norm of just the map dp that eats a simple function. What is this? Well, it's the supremum over all the f you can take, and we take all the simple f, right? So simple over all simple f, and we calculate the norm integral f dp over the norm of f, and on that space we have the supremum norm. But what is this norm? This norm here, what is that? So what is the result? The result is an operator from h to h, a bounded operator from h to h. So this guy here, this norm, is actually the operator norm on LH. So this operator norm is given by this operator norm divided by this. So this is the sup of all simple f of the sup of all psi in h for the norm integral f dp as it acts on a Hilbert space element psi. Now this is the norm on a Hilbert space, but you need of course to divide by this norm on a Hilbert space, and there's still this norm left from before. Now the point here, if I may go back to this estimate here, this estimate, so this is true for all f simple and for all psi and h. But in fact, this equality is assumed if you choose the psi and the f right. Okay? So that means here, the ship this guy here is always less or equal to that guy there. So the ship, because the equality is assumed, the whole thing is equal to f times psi by f times psi, and that is 1. So we indeed calculated this operator norm here, and it's a bounded operator. And what about, so integral FDP is a bounded operator by construction, but this one is a bounded operator too. It's the map that takes a function and maps it to a bounded operator, and that map has norm 1. Okay? Extend the whole thing to integration with respect to a projection valued measure of a bounded Borel function. So far we had only simple Borel functions, but now this is a very easy step. Consider the space B of R. We didn't have this space yet. The space B of R is the space of Borel measurable functions f from R to C, so that are measurable, Borel measurable, and that the supreme norm is less than infinity, and that's exactly the boundedness, right? So if we talk about bounded here, we talk about this condition here, okay? And this guy here is actually a Banach space, which is, in fact, a Banach space. So it's complete. It's complete. And observe that the set of simple functions, fr to c simple, is obviously a subset of B of R, because our notion of simplicity, as I define it, includes measurability. It really, if they take only finitely many values, certainly the supreme norm is finite. Okay? So these are a subset. In fact, is a dense subset. It's not only a dense subset, it's even a dense linear subspace. Obviously, this is a vector space. You can add them pointwise, S multiply them pointwise. And the simple function is the same, so it's a dense linear subspace. Aha! What do we know? So we have, so let's give this step on the right-hand side the name, let's call this the simple functions over R. Okay? So we already have, from A, we have a map EP that takes us from the simple functions over R into L of H, the way it's given. And now we have here a Banach space, B of R, in which this lies densely. What do we know? Well, we know that there exists a unique extension of the previously defined integral BP map to this, according to which theorem? Which theorem guarantees that if you have a bounded, you see the map is bounded, you have a bounded map. ELT, that's it. ELT says, because indeed the integral dp has norm 1, in particular it's bounded, so the bounded linear transformation theorem, the BLT theorem, guarantees there's a unique extension. And this unique extension, again, will have the same norm. That's part of the BLT. In other words, it is zero work once you understand for the simple functions, you need for all bounded Borel functions. Okay? It's just the same, just approximated. That's it. The BLT theorem says there's a unique extension, take that one. Okay? Thus we understand how the dp guy acts on any bounded Borel function. The Banach space with bounded Borel functions. And from the Banach space of bounded Borel functions, we are sent into the Banach space of bounded linear maps. This is the Banach space, for a different one, of bounded linear maps, which therefore can always go from H to H. So we integrate over a bounded wave function from f from R to C, we apply this, and what we get is a bounded operator. That's nice. I will emphasize bounded wave functions goes to bounded linear operators. Well, because as soon as we drop the boundedness condition, as we must in the next step C, we will no longer get bounded operators. So integrating, although the P's are all bounded, but if you then integrate over an unbounded wave function, the result will be an unbounded operator. If it's unbounded, it's no longer defined in all the H, and then all hell breaks loose concerning domain issues and so on. And that will then actually lose the linearity that this array still has. Okay, that's only the next step. Let me give you three properties that this map has at this stage. With the properties, so that can be shown, of course. The first property is, always forget this one, that's why, yeah, of course. If you integrate over the one function, well, that is certainly a function that sends everything to the one, then a real number to the complex one, that I could have written down earlier, that's giving you, if you integrate over all of R, you will get the identity on H. Yes, that's what it must be. That's the identity on H. The second property is the following. Integral over all of R f times G. You see, the space is not only a vector space, it's even a Banach space. It's a Banach algebra because you always also have a multiplication on it. So if you integrate the product of two functions, then what you actually get, that's maybe a little surprising here, but that has to do with the projected quality of the P, as the integral FdP after the integral GdP. Isn't that funny? Isn't that a very funny rule for products? Because the P is a projector. That's why we get this. Okay? That's number two. And then there's property number three. I squeeze it down here. It's also very useful. We'll need it again later today. Integrate over all of R. If you integrate over the complex conjugate, well, you have f is a function from R to C. You can certainly take its complex conjugate and then do the projection valued integration, or integration with respect to the projection valued measure. Well, what that is, and will be very useful, is integral FdP without the bar. That's an operator, a bounded operator, and it's the adjoint of that. Conversely, if you have an operator represented this way, and you want to take the adjoint, well, simply take the complex conjugate of the f here. Ah, that's good. Okay. And these three properties together, 1, 2, 3, there is some terminology for that. Well, there's a linear map. Yes, again, this is a linear map, because here the linearity is still there. That's linearity that will drop later. Now, 1, 2, 3 together for such a linear map, there is a saying, there's a terminology for that. One says integral dp is a C-star algebra homomorphism. What's that supposed to mean? Well, this is a Banach space, and this is a Banach space, so it's a vector space homomorphism, well, it's a linear map, but then it also has a product on here, which is the pointwise multiplication of functions, and it has a product over here, which is the composition. It also has a star operation over here, which is the adjoint. It has a star operation here, which is the complex conjugate, okay? And so if you have here a Banach, you have a C-star algebra here, a C-star algebra there, and these properties, especially 2 and 3, say that the product and the star are preserved, mapped to each other, so it's even a C-star algebra homomorphism. If you want to scare little children, you say that. If you want to calculate, you just note what it means. Okay? And this is all so nice. I mean, this is all so nice and so useful for us, because we cannot restrict ourselves to the bounded wave functions here, hence we will not have the bounded operators on the right-hand side, and that is what we're going to do next. So let's continue. So, final step, what we actually want to arrive is integration with respect to a projection valued measure, but now of an unbounded, so that means not necessarily bounded, of an unbounded Duell function, Duell measurable function, f. So now, integral dp was seen so far to send a bounded Duell function. So that means f in the set B of R to a bounded operator, which was then called integral FdP, because it's bounded is in this case. We will now define the following thing. Definition. Let f be an unbounded, well, I could just say a measurable function. F, a measurable function from R to C. the order assumption. We started with simple f, we extended by B and T to bounded f, bounded below measurable f, and now we drop all the conditions. The f be any measurable function. That's what we need for quantum mechanics, for spectral theory, for exponentiation of operators, for just anything. We need this. Okay, finally realized that let f be a measurable function from R to C. Then we define the linear map. But now careful, I do not define integral dp as it is a measurable function because I can no longer. I have to immediately define the result. I can define integral f dp, and this is a linear map from where to where. Well, this is going to be an unbounded operator. Before it was bounded, if the f is unbounded, this entire operator is going to be unbounded. If it was bounded, it would go from h to h. If the f is bounded, this is such a map, right? But now the f is unbounded, and I tell you, in that case, the domain of the map. The domain of the map is not the entire Hilbert space. Okay? Then we define the following linear map, whose domain depends on the map. And where? On V, and now come two claims which have to be proven. On dense linear.
It's been measurable, but it's for every measurable, so
any measurable f you can take and define this object.
I'm thinking about that because if you take a bounded, is that
yeah, if it's bounded, but now we never have a bounded f. And then the whole operator will not be a bounded operator, hence it will be only a subset.
Because you can be assumed that it's a bound. So
yes, okay, so okay, I made a pedagogical point here. So in general it will not be assumed, okay, but I should not exclude and can be assumed. Okay. So on the dense linear subset, so if I define a map, I need to tell you the domain and I need to tell you the prescription. On the dense linear subset, D sub f dp r. So in literature, people don't also write D sub f because actually everything, but it's better to write it like this because D sub f sounds like the domain of f, which is the domain of this object. This subset is given by the subset of the Hilbert space, all those psi in the Hilbert space that satisfy an additional condition, namely the condition that the absolute value squared of f with the d mu psi integrated. So that's why this becomes a condition on the cell, and f is given because it's the given one over which we integrate, but that is finite. Okay, so we define this linear map on the dense linear subset, so I gave you the domain on which it is defined, and now I need to give you the prescription. Well, that is going to be interesting. Defined on this by virtue of, so I take a psi from this domain, and I send it to over here, so I need to send it to a Hilbert space element, and I need to send it to this object which, once I'm finished, once I defined it, well, that is trivial, it's the map as it acts on psi, right? How is it defined? It's defined as the limit of n to infinity of the integral fn dp as it acts on the psi, because this is a map, and then the limit is taken after I acted on the psi, so this is a limit in h, because this whole guy here, the whole square bracket, is are elements of h, so this is a limit in h. We know what convergence means. The only thing I haven't shown you yet is how the f is defined, where now we say, define the integral by writing down the integral, but be careful, this is the integral over fn, where the fn are defined as a characteristic function multiplied by the unbounded f, so this is the unbounded, possibly unbounded f, so the possibly unbounded, or I could say the unbounded f, and now I want to convert the unbounded f into a sequence of bounded f's. How do I do this? Well, I just cut it. I cut it at higher and higher and higher and higher levels. Okay? So if you have a function like this, you can make it into a sequence of bounded functions by first cutting it at level 1, so you have to take the absolute value and so on. So that would mean you cut it here, so if this is f, now you cut it at level 1, and then you get this this 0 1, then you cut it at level 2. At level 2, then you get this group 1. And so on, with a sequence of bounded functions. Of course, if you follow them, you will cover the whole thing. But what are those? Well, it's the characteristic function of the set all the x in the domain of f, all the x in R, such that x is bounded is less or equal to n. And that means these guys. So the is f1, and the green one is f2, and so on. Okay? So where the tralala are a sequence fn that lies in the bounded Borel functions. Well, you can see it, then the bounded Borel functions. So that's it, that's the definition, those guys go into here. So the only question is there convergence to F where you can show that these Fn's are a Cauchy sequence in Banach space. Hence, okay, proof. Show that Fn is Cauchy in Banach space